My name is Grace. I'm a PhD student at Clemson University in the Civil Engineering Department. I know we're kind of short on time, so I'm going to try not to ramble too much, but this presentation is going to be a little bit different from some of the others. Rather than talking so much about like existing concrete structures, we're going to kind of introduce a new structural system that is designed with a lot of the concepts that Julie discussed in her presentation in mind. So I think I can get into that a little bit later, but I do think her presentation tied in really nicely with this one. So hopefully you'll see some parallels there. Firstly, I just want to acknowledge some of the research collaborators that have been really involved with this project. I work especially closely with Dr. Kleiss and Dr. Ross at Clemson. They're the PI and co-PI on this project. And then we also collaborate with Drs. Okumish and Khorasani at the University of Buffalo. This whole thing is kind of all their brainchild. So I'm just helping bring it to fruition. And this entire thing is funded by the NSF. I know Dr. Ross is in this session because he's been pretty active in the chat. So he might be able to help answer some of your questions while I'm talking in the interest of time. No pressure, Dr. Ross. If you don't want to, you don't have to. And so let's just kind of jump in. So first, I want to tell you guys what we're going to be talking about today. So firstly, we'll just do kind of an overview of what TESA is. I know in the title it just said Tessellated Concrete Structures, but as an acronym we use TESA. Just less of a mouthful to say. So I'll explain what exactly that is to you guys, what its benefits are, and what the objectives of our entire research project are. And then I'll show you guys the specimen. It's a TESA wall. And again, once I explain what TESA is, you'll maybe understand what I'm talking about. And I'll show you how we designed and constructed that specimen. I will briefly go through the reverse cyclic loading test that we did. I have a very, very short video of it you can watch. And then we'll talk about the test results and how that relates to ACI's criteria for acceptance of shear walls. And at the very end, we'll just look at kind of where we're going next with this project. So like I said, first of all, we're just going to talk about what exactly TESA means. So TESA, in order to understand it, we have to understand first what tessellations are. And tessellations are simply repeating geometric patterns with no gaps or overlaps. So this would be an example of a very simple tessellation with elements that do not geometrically interlock. So we would call this a non-interlocking tessellation. And like I said, there's no gaps or overlap technically in like the mathematical definition of a tessellation, but when they're used architecturally, it's a little bit looser of a definition. They often will include gaps, as you'll see in one of these examples. So tessellations have been used just as an aesthetic feature for a really long time in architecture. Some pretty contemporary examples include the Al Bahar Towers in Abu Dhabi. As you can see, there are some gaps in this tessellation. So like I said, there's kind of a loosened definition when we're talking about architectural examples. And then another example would be the Mulberry House in New York City. This one is a little harder to see the pattern, so I outlined it for you here. They're kind of L-shaped precast panels that have a brick inlay. And again, these don't serve any structural function. The one on the left is simply a light controlling facade, and the one on the right is just purely aesthetic for the panels. It's just a facade. Which brings me to the difference between TESA and what has formerly just been used as an aesthetic feature for the most part in architecture. TESA stands for Tessellated Structural-Architectural Systems, and these tessellated elements are load-bearing. So that is where the engineers kind of come in. And we have a couple different possible kinds. Today, we'll specifically be looking at a one-dimensional interlocking tessellation. And all that means is that the individual elements of the tessellation are able to translate in one direction, but they are interlocked in the other. Whereas with a two-dimensional interlocking tessellation, like the one on the right here, this tile is prevented from moving in two directions, vertically and horizontally, just due to the interlocking nature of the geometry. So again, today we'll be looking at one-dimensional, like the one on the left. So this is kind of where I mentioned that Julie's presentation tied in really nicely. I know she briefly mentioned circular economy. One of the big benefits of TESA is that conceptually it contributes to the circular economy really well, and specifically it lends itself kind of to this bottom third of the circle in the circular economy model. So if you're not really familiar with the circular economy concept, it's just a regenerative system where you use the waste from a process as the input for another process. So your waste becomes a resource. And specifically, TESA systems are designed for repair. So that's kind of in this green section of the circle here. The whole idea behind TESA, where the idea kind of originated, was that if damage occurred, and specifically in concrete tessellated systems, the cracks or spalling or whatever it may be, the damage in the concrete would not propagate across the boundaries of each individual element of the tessellation. So then the tiles could individually be removed and replaced without having to replace the entire system. In addition to that, they're also designed for disassembly and reuse. So like when Julie talked about the component harvesting, essentially these, specifically we're talking about walls today. So these walls are designed to be taken apart and rebuilt essentially. So probably in the real world, you'd be more likely to have this kind of a situation where you're rapidly repairing it just by replacing a couple of tiles, but you would also have the option of disassembling a wall and reusing all of it or part of it somewhere else for another purpose. A couple additional benefits of using a TESA system would be that it lends itself really well to automated construction and fabrication because of the repetitiveness of the tiles. Since they're identical, they can be quickly manufactured and constructed. And then also kind of the obvious benefit would be the architectural appeal. This is an example of another architectural tessellation that already exists in Paris. And it's very appealing to the eye. Architects are pretty into it. We've got Skidmore, Owings and Merrill as kind of a partner on this project. So the architects are pretty into this idea. There's a lot of freedom with the different patterns they can do and things like that. So specifically for our research project, the objectives are numerous. I'm not going to go into detail with all of them, but we've recently presented at a conference in detail how we fabricated and constructed this test specimen that I'm going to briefly talk about. So you can look for that paper if you want more information on that. Our counterparts at the University at Buffalo have been specifically investigating the numerical analysis of these walls. So there has been recently a paper published that this figure was taken from that you guys can take a look at if you want. Specifically today, we're going to be talking about the performance of the physical test specimen at the lab at Clemson that we did. So now we're going to look at how we put that specimen together. So this is kind of the conceptual rendering for the TESA wall. It is 6 feet wide and about 9.5 feet tall, and all of the tiles are 5.5 inches thick. As you can see, we picked this repeating eye-shaped tile, but there are a few different shapes needed to form the boundaries of the wall. And then this is what the wall looks like in real life. We did not stray far from this conceptual design, as you can see. The individual tiles are reinforced with number 3 rebar, and they have PVC pipes that run through them longitudinally. And that's a place for unbonded post-tensioning to run through continuously through the height of the wall, just to provide some like global reinforcement ductility. And the tiles themselves are about 2 feet tall, about 1.5 feet wide. And the tiles could be scaled up to pretty much any size you want. These were kind of the smallest tiles that we could design while we still had 2 planes of reinforcement and confined concrete. Tyndall casted all of these for us, and they just used kind of their standard production mix. So these are pretty typical precast values here. In terms of constructing the wall, before we could actually build the specimen, we had to design a test frame. So that's what you can see now. We have a base at the bottom that transfers the lateral loads from the wall to the test floor. And then there's also some lateral bracing for any out of plane movement of the wall, as well as just some safety guards kind of on the side for during the construction process. And then we had to figure out how we were going to lift these roughly 100-pound tiles because obviously lifting those up 9.5 feet in the air isn't really something you want to do manually. We decided to use a chain hoist. So we just had Tyndall put some PVC pipes that ran through the thickness of the tiles so that we could put some lifting rods through there and use a chain hoist to lift everything into place. And finally, we were able to stack the tiles row by row, and we maintained about 3/8 of an inch of space in between each tile, just so we wouldn't have concrete bearing directly on concrete and would have a little bit of construction tolerance. And we just grouted in those spaces to maintain the leveling and transfer the compressive stresses between the concrete tiles. So quickly, I will try not to get too into the results, but we are going to briefly just talk about how they relate to ACI's requirements, because I know you don't want to be here till like, you know, I don't know, an hour from now, and I could talk about it all day. But this is the test setup for the actual reverse cyclic loading that we did. We've got the unbonded post-tensioning that provided a clamping force. It was a compressive stress of about 6% of the wall's capacity. The actuator that is attached to this actuator frame, the orange frame, is what provided the push and pull for the lateral loading. The base at the bottom has these little toes, that's what we call them, toe pieces, that provide some shear resistance. And then of course we have the base that's bolted to the floor to transfer everything down to the slab. And we've also got these post-tensioning strands as well as bolts on the base that run through the bottom tiles of the wall that resist the moment from the lateral force. So that's how all the forces move through our test setup. So the way that we designed kind of our load cycles for the displacement protocol for this test is using this ACI document that's referenced here. It's kind of a mouthful, but essentially it is the test design for precast walls with unbonded post-tensioning that don't meet the criteria for ACI 318, which is about the closest thing that you could say relates to our specimen. It is kind of unusual, but this fits it, that description fits it pretty well. So the way that that document explains to design your displacement protocol is to start with some small percentage of what you expect your maximum capacity might be, which was a little bit of a challenge because there wasn't a defined analysis procedure for this type of wall to figure out what we thought the maximum capacity would be. So we used some results from our friends that are doing the numerical modeling at University of Buffalo to kind of eyeball what we thought the capacity might be. And then you just kind of stair step up incrementally for each set of load cycles until you get to a maximum drift capacity that ACI defines for a wall with your aspect ratio. So each little set of load cycles is comprised of 3 pushes and pulls. So a push and a pull would be 1 cycle, and each set has 3 cycles. And for our specific specimen, the maximum drift angle defined by ACI, they give you a little equation based on the height and length of the wall. it came out to 1.73% for us. And what that means is that we were going to continue increasing our displacement incrementally until we either got to this drift angle or saw failure. And failure can be defined in a couple different ways. Kind of the most easy to see right off the bat was a strength reduction of 20% of the peak load. But we got past this drift angle, and since it was kind of a new system, we wanted to keep going just to see how it would fail. So we ended up going to almost 3%, I believe. We'll see that in a minute on a different slide before we actually saw a failure. So next we have a little short time lapse of the final cycle of our test. So, oops, try not to move my mouse too much so it brings up that bar. But as you can see at the beginning of the test, you can see the push and the pull motion. At the beginning of the test on the bottom right, we already had some spalling from the previous cycle. And then you can see a pretty sudden spalling at the bottom left corner. And that was when we decided to stop the test because our strength really dropped at that point. I'm sure you'll notice that the frames are moving. We did monitor the displacement of the frame so that we could correct for the displacement of the wall and make sure we were only recording that displacement for our results. So this is our hysteretic loop for our wall. This is the load displacement response. It makes a very pretty graph when you're done. And I've gone ahead and outlined the backbone curve for you. I didn't include the failure at the backbone because that is where our failure at that bottom left toe of the wall occurred. And our peak load in the push direction was about 81 kips. That occurred in the second to last cycle set. And our peak drift angle was about 0.03 radians, which comes out to roughly 3% drift. And in the pull direction, our peak load was about 85 kips with roughly the same drift angle. One of the requirements, as I mentioned before, that kind of tells you when you've had a failure is that your strength doesn't reduce to less than 80% of your peak load. So for example, in the push direction, the second to last cycle had the peak load of 81 kips. 80% of that is at this orange dotted line. So if our last peak load had been below that, that would have been the end of testing because that would have been a failure. We didn't have to even compare anything in the pull direction because the peak load was the last cycle anyway. So one of the ways that we can kind of quantify how much energy is dissipated by a structural element under cyclic loading is by calculating this relative energy dissipation ratio, which means you can then compare it to another shear, for example, a shear wall of any size, and be able to actually compare how much energy they dissipated relative to their size rather than having to figure out how you're going to compare. I don't know if I'm articulating this well, but when you have two different size walls, they're probably going to displace a different amount, right? So by doing a relative energy dissipation ratio, you can compare the two, is what I was getting at very poorly. So the way to do that is to find the area of your last hysteretic loop. So this is my hysteretic loop for right before failure, essentially. Found the area for that. And then you create kind of this imaginary parallelogram that has side slopes that are the initial stiffness that you saw in your specimen. And if you divide those areas, you get this relative energy dissipation ratio that needs to be at least 0.125. Less than that could lead to like fatigue failures and issues with that. So ours came out to be 0.158, which is desirable because it is greater than the minimum. Another kind of quantitative thing that we can look at is the secant stiffness of the wall and how it decreases throughout testing. And ACI in that document says that they want no stiffness below 10% of the initial stiffness, or else that would constitute a failure in testing. So our final cycle was just barely over 10% of the initial stiffness. Any lower and it wouldn't have been included in our results. But as you can see, the stiffness decreased pretty regularly throughout the entirety of testing. This is another graph that's very pretty, and everybody, it's like a pretty butterfly. My husband really likes this one, even though he knows nothing about engineering. So this is just the graph of the post-tensioning stress throughout testing. The solid lines are the outermost strands that we actually had load cells under, so we could calculate the stresses. And then the inner strands were all calculated just based on theory and the assumption that the stress was a linear distribution throughout the wall. And one of the other acceptance criterias is that at half of the maximum drift angle that we found at the very beginning when we were talking about load protocol, the stress in any strand shouldn't exceed 90% of the yield stress, which is a mouthful that basically means between these two black lines, none of these graphs should go above the orange line. So we met that criteria, which is good. But you can see that these two outermost strands did yield in the very final cycle set. So that was, that was when we stopped testing. So that I'm sure led to the ultimate failure or imminent failure of the wall. So these are just a few pictures of the damage at the end of testing. As you can see, we had pretty desirable behavior in terms of the damage being isolated to just a few tiles. There is, you can see where we marked with Sharpie some small cracks throughout the wall, but the major damage, like in terms of spalling, was all at these corners. And that is kind of visible here in this graphic that just shows you we didn't have any visible damage until after cycle 8, which corresponds to around where we hit that maximum drift angle that ACI defines. So that's nice that we didn't see a lot of damage until we got to that maximum drift angle. And then you can just kind of see how it developed throughout the rest of the cycles. The red cracks are new cracks and the blue are existing from previous cycles. So we didn't really have much spalling until cycle 10, and then cycle 11 obviously was getting pretty bad. And using some FEMA documents in conjunction with our results, we made some damage categories for our TESA wall. And we just did this to help us define how we were going to decide what tiles needed replacing. So these are our categories and our repair methods and the crack sizes that constitute a category. And then this is just a development of the damage in terms of these categories. So a darker color corresponds to a more severe damage category. So for example, in cycle 11, there are some black tiles. Those mean that those tiles are spalled. So we decided we were definitely going to replace any of the spalled tiles, with the exception of the top corner, just because of logistical problems with the test setup. We weren't able to reach that one. So we ended up just repairing that one with a lot of epoxy and a carbon fiber wrap, which you will see in a minute. I'll show you some pictures. So our conclusions can kind of be split into the sustainable, resilient design conclusions and the test conclusions, because we did kind of hit both ideas in this presentation. But the highlights are basically that we can replace individual tiles to repair this without having to repair an entire wall. We can just, or replacing it, we can just replace a few. We can reuse our already fabricated tiles somewhere else if we choose to. Again, maybe not as likely as the repair application, but it's possible. And then of course we can recycle any damaged tiles. There were some sessions earlier in the week, I think, on recycling concrete materials, and this would certainly be a good application of that. And then in terms of our specimens acceptability according to ACI's requirements, We exceeded the minimum energy dissipation ratio, so that is good. We also stayed within the limits of the reinforcement stress during testing. Again, these are all things I already talked about, but the peak load never dropped below 80% of the maximum load once the maximum load was reached, and the secant stiffness never dropped below 10% of the initial stiffness. So that just essentially means that all of our data is for before failure. And these are all good things in terms of acceptability, which is definitely a good sign for this system being used as a shear wall. So just really quickly, I told you I would tell you where this is going. I was hoping originally when I submitted this abstract that I'd be able to talk to you guys about the repaired results, but unfortunately, I'm sure many of you are familiar with how testing goes. We haven't gotten there yet. So hopefully we're going to do that test in the next month or so. But we have repaired it, so I can at least show you some pictures of the repair. On the left here, you can see the wall missing the tiles that got severely damaged either during the testing or when we were trying to remove the severely damaged tiles. I think a couple of them ended up having to come out because we butchered them pretty badly when we were removing their neighbor. And then we were able to slide new tiles into place and grout around them. So this is our repaired wall that's ready to be tested again. This was not very easy to do, but my qualifier for that is if you were an expert in concrete construction, you'd probably have a lot better idea of what tools to use and what the best strategy would be, rather than us kind of, experimenting, trial and error, what was the best way to get these out. So I think if you had kind of a skilled tradesperson, this would be much easier. And I'm happy to answer any questions about how we did that, but in the interest of time, I will skip that for now. So again, my name is Grace Crocker. If you guys have any questions or want to discuss this with me, I know we're over time already, but you're welcome to send me an email, and I'm happy to talk to you about it. So that's it for me.